Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about electromagnetic induction. Now electromagnetic induction is the process of creating a current in a circuit loop by changing the magnetic flux. Basha, we said that as long as there is a relative motion between the magnet and the coil, EMF will be induced. But for current to flow through the circuit and to be induced, then the circuit must be closed. And we also talked about the EMF induced for a straight conductor. Good man, if a conductor it is moved inside a magnetic field at some angle or at what angle, then EMF will be induced. Good man, equation kadakata BLV sine theta, Basha. And we said it's maximum if the angle between B and V is 90, it is half. If the angle is 30, it is 0 if it is moved parallel. Today we'll talk about more of that, Basha. We'll talk about the number, and the change in the number of magnetic field lines induce a current. What exactly this kaka? Man, there are 4 methods we can induce EMF with, Basha. And good man, you can move the magnet closer to the coil, or the coil closer to the magnet. This doesn't matter as long as there is a change in the magnetic field line. So there are 4 methods, Basha, 4 ways we could do this, Baba, to induce EMF. Basha, what are these 4 methods we're going to learn at this lesson, inshallah? So the first one that we have, it says ways of inducing current in a circuit. Good man. The first one is if a circuit is moved into or out of a magnetic field. All right. If a circuit moves into or out of a magnetic field, the magnetic flux on a coil on a circuit is changing. That induces EMF. If a coil is moving into or out of a magnetic field, if the circuit is magnetic field moving onto the coil away from the coil, it doesn't matter whether the circuit is moving, the coil is moving, or the magnet, doesn't matter as long as there is relative motion between the two. That is for second. We can say that it is by rotating, if the circuit is rotated inside a magnetic field, or if a coil, in our case, for example, if it is rotating inside a magnetic field, that also induces EMF. How is rotation, kaka? Because once you rotate the coil, Baba, the angle between the magnetic field line and the area will change. That also, it can change the magnetic flux, which also induces EMF. Another method is by increasing or decreasing the intensity of a magnetic field line, or reversing the direction of a magnetic field line. When we say changing the intensity of a magnetic field line, magnetic field line strength magnetic field, which is the magnetic field line or the number of magnetic field line that are crossing the cross-sectional area here, or by reversing the direction of a magnetic field. Basha, how do we do this? Basha, there is a method. I'll explain how we could do that, Basha. And then the 4th method here, these are, by the way, 3 methods that are mentioned directly, Baba. It is not mentioned directly, but question that it talks about changing the cross-sectional area, even though this is the least practical. Also, this is another method of inducing EMF, and that is by changing the cross-sectional area. Cross-sectional area, the number of magnetic field lines that are passing and crossing the cross-sectional area will also change. Magnetic field line that means, or the angle, that means the EMF will be induced. Regarding 3rd one, Baba, how can we increase or decrease the number of magnetic field line? Let me talk about this a little, Basha. All right, so again, Baba. In the in chapter 5, let me talk about this a little. In chapter 5, that's from the previous one. If we have a coil or a solenoid, if we increase, let's say, or decrease, so let's talk about this one here. Let's say, all right, here's a battery, one side positive, negative. So there is current flowing through a circuit here. Here we have a variable resistor, Basha. This is a variable resistor. And this arrow, Baba, that means this is variable, you can change its value. Okay, Basha, so at this point here, for example, once you turn the switch on, of course, a current passes and flows through the solenoid here, so there will be a certain magnetic field around it. So here a certain magnetic field around this one here. As we know that the relation between current and resistance, it is inversely proportional. So agar resistance kam kaino baba, the current that is flowing through the circuit will increase, Wrya, because these two are inversely proportional. What does it mean? That means the number of magnetic field lines are going to increase, Wrya. And consider this, for example, so the number of magnetic field lines here. So let's just consider that the direction of a magnetic field, so this side is north, and the other side is south. Got the direction of magnetic field. Okay, this is how it goes here. Later, we can see that the direction of a magnetic field line is going to be this. I think it would be best if we just reverse this one here, so that it makes better sense. Part of it, this one here, magnetic field line, you can see that they'll extend. So by increasing the strength of a magnetic field line here, magnetic field that are crossing this coil here, that is going to increase. By increasing the current, strength magnetic field intensity magnetic field line on this coil here increases. This is how we can increase or even decrease the number of magnetic field line. Will increase the resistance. Agar resistance زيادة current كم دبيتو magnetic field line of course will also become less. Now at this point here, less magnetic field line will pass or cross this coil. This is how we can increase or decrease the strength of the intensity of a magnetic field line. At the reverse direction, you could just switch the polarity of this battery. Positive, negative, you can change the direction of a magnetic field at this point here. These are four methods of four ways of inducing EMF. Let's summarize them one more time. By moving the circuit into the magnetic field, out of it, moving the magnetic field line onto the circuit and away from the circuit. That is first. Second, by rotating the circuit coil and circuit. Third one, by increasing, let's say, the intensity, decreasing the intensity of a magnetic field line or the direction of a magnetic field. And then the fourth method was by changing the cross-sectional area. These are four methods of inducing EMF in a circuit coil here, or in a circuit like in general here. Talks about this one here. It says by using, I forgot to mention actually here, this variable resistor here in physics, we call this one a rheostat. Rheostat it's a variable resistor. Resistance all right, so that can change the amount of current that is flowing through the circuit. By using a variable resistor, rheostat, the following can be made. A change in a resistance, the current strength magnetic field strength the electromagnetic chapter 5 suppose you have two circuits, as you can see here. One of them consists of an electromagnet. Electromagnet chapter 35 electromagnetic we can say the first circuit a DC EMF source a DC electromotive force and a DC potential source here, and a variable resistor that permits or allows you to control the strength of a magnetic field. In the second circuit, you have a coil, only a coil of wire, and a galvanometer. So list three ways that the induced current or can induce a current in the second coil. Method basket. Three of them can be used here. Actually, all of them can be used here, but the question is only asking for three, so you can count three just to, for example, say how the current will be induced here. This is the circuit that we have. DC source, you can say here, and then there is a variable resistor, rheostat, as that once you close the switch, there will be a magnetic field around this coil. This coil here, it can be used, so you can pretend or treat this one here the same as a magnet, you could treat this one the same as a magnet, with the north and south. It doesn't matter at this point which side is north and south at this point here. We can move this, it doesn't matter which one you move at this point. You can move this coil closer or away from this. by moving this coil closer or away from this, or this electromagnet closer or away from that, that induces EMF. That is the first method. Second method is, good man, by rotating the coil, Baba. It doesn't matter which one you rotate. Let's say we're just rotating this one. By rotating this coil here, you can induce EMF. That is two. Third one here, good man, by increasing or decreasing the intensity, the number of magnetic field line. Kujmari magnetic field line kan ziyada kam daki Baba, by using this rheostat or variable resistor. Agar resistance ke kam kiya, أو كاتي كرنت كزياد دبي كرنت زياد بيتن electromagnetic and bubbling magnetic field كان زياد دبي, which means that EMF will be induced here as well. That is the third method. أجد داوي رجعت سعره مشان كده بعد ما نقول by changing the cross-sectional area أو كاتي دبا أو كل هندك you had to apply force on it to make the cross-sectional area smaller or bigger. But like we said, this is the least efficient كزور أو طريقة زور عملية باشا. Moving the coil into or out of it, by rotating the coil, by changing the strength of a magnetic field, by adjusting the variable resistor or rheostat. Why does moving a conductor inside a magnetic field induces EMF, Basha, or electrical current, but moving an insulator in the same field it does not? Like we said, if we move a conductor inside a magnetic field, EMF will be induced. Because this conductor has a lot of free electrons in them. So once you move them, there will be a magnetic force on protons and electrons, right? Clearly, right? If there is a magnetic force on these electrons and protons, now, Gutman, electrons will be pushed to one side. Let's say protons will be pushed to the other side, even though we'll just say this, Basha, so you understand. They don't move actually, Basha, but there is still a force on them. So one side becomes positive and negative, right? So this is how we can induce current, we can say. But because in insulators, we don't have any free electrons. If there's no free electrons, there will be no magnetic force on it. If there's no magnetic force on it, that means there's no induced EMF or even current. Free electrons in the conductor experience a force due to the changing magnetic flux. And the magnetic flux is changing. These free electrons will experience a magnetic force, which makes them move right through the conductor. But in insulators, creating a flow of charge. In insulators, lack of free electrons or the lack of free electrons, so no current will be induced. It says, which of the following way can induce a current inside a closed circular loop? There are four methods. By moving the circular loop in or out of a magnetic field, that is true here. By changing the magnetic field strength or direction around the loop, that is also true. By rotating the loop inside a magnetic field, that is also true. At this point, we can say all of them. These are the kind of questions that will bring you in Wazari regarding this. We solved the other question here. It says a wire conducting AB, with ends AB, you can see here, moves at a constant speed in a magnetic field B, as shown in the figure. Which of the following is correct? أنا delay induced EMF لا ADB to positive or AD negative بونوي. Now, first of all, before we look at the choices, let's just take a look how it is. كتمان direction motion كي لخواري magnetic field دكا. It is a point, which means out of the page here. If you do this, Baba, that is out of the page. Direction motion كي لخواري كاتا. This side would be positive, أو لا HDB to be negative, because that would be the back of hand. In other way, Kaka, or other words, we can say A will be positive and B will be what? Will be negative. Kata, which one of, and obviously that is EMF induced. Current induced. Because in order for current to be induced, Kati to be closed circuit activity, which we don't have here. The first one says induced EMF is generated. Basha, induced and generated is basically the same thing. That's not a problem. Good man, EMF will be induced. Bash kaka. Man, A is positive, A becomes the positive pole and B becomes negative pole, and that matches our work or description here. What about B here? EMF will be induced or generated, but A is negative, which is incorrect. B is positive, that is incorrect. Man, C says induced EMF is generated. A is positive and B is positive. Not going to do positive. Man, habitin baba. Kata C is incorrect. No induced EMF is, no EMF is induced here. Kata, this is incorrect. Kata, the only correct answer is A here. Basha, what about question 3 says, which of the following actions will induce an EMF in a conductor? Move the magnet or a magnet near a conductor. This happens, Basha. Move the conductor near a magnet. Good man, this also happens. Man, it doesn't matter which one you move, the magnet or the circuit, the conductor, the coil, doesn't matter. C says rotate the conductor. That is also true. And yeah, D says all of them, so this would be the correct answer here. Basha, all of them are correct. Characteristic of induced current. Basha, characteristic property of current induced debitan once we move a magnet close to a bubble in a coil. Basha, and by the way, who said this? Lenz said this. So you can, or on this one here, you can say the Lenz's law as well. Basha, Lenz's law. You can add Lenz's, Basha, Lenz's law. وطبعا بابا بتشتري بس ما كتمان بهيس نوع كرنت درزنابي حتى إما فكي كم زال درزنابي باشا ك بابلين positive و negative كان once they pushed to different sides of the wire conductor, that is called EMF. ونيا حتى إما فك درزنابي, then current or no current will be induced. So the lane characteristic of the induced current كرنت كدرز, of course the B comes out EMF كدرزبوبي, then after that the current will be induced, Basha. Or you can say this two happens simultaneously, as long as, not simultaneously, I mean as long as EMF is induced, then the current will flow through the circuit. So what exactly happens once we bring a magnet or move a magnet close to a coil or away from a coil? We'll talk about each one of these in details, inshallah. So let's begin with the first one here. Basha. So the first one that we have, once we move a magnet close to a wire, a coil of wire. Basha. So first, let's say we have a magnet, Basha. Here's a magnet, and we have a coil of wire. Yeah, a magnet here with north and south. And here's, let's say, a coil of wire, or you could say solenoid, doesn't matter. Later, this is what we have. I believe it is best if we change this color. That's not a problem. We will use a galvanometer, by the way, just to see, for example, how the current is induced and which direction to. One side is positive, like beta negative, and that's what it is. So what exactly happens, Baba, once we move a magnet close to a coil? Obviously, there's a magnet. When you got that, there are magnetic field lines. A magnetic field line, and they always go from north to south. When you and of course, there will also be magnetic field lines here as well. Now here's a coil to here. And bubbling cross-sectional area of this coil right here. So what exactly happens as we move this magnet close to this coil here, Baba? Let's move this magnet closer to this coil here. I get magnete, Baba. If we move this magnet closer to the coil, I get to as the magnet is getting closer to this, magnetic field line that are crossing the coil, does it increase or not? It changes, right? Or you can say that it increases when if the number of magnetic field lines that are crossing a cross-sectional area changes, so the twanin, according to this, we can say that the flux, Basha, flux is changing here. Basha, magnetic flux is changing. Magnetic flux or magnetic field line that are crossing through a unit area. Basha. We can see that magnetic flux is changing, and you can see that here the strength of magnetic field inside the coil we can say that the magnetic field line or the intensity of magnetic field line inside the coil increases. Basha. But as the magnetic flux is changing, Baba, because there will be actually a magnetic force on a bubbling charges that are inside this wire here. So magnetic field line Baba would be, or there is a magnetic force because of these magnetic field line and their charges here. There'll be a magnetic force on these charges. Now this magnetic force produces an EMF. أو EMF produces a current in a circuit here. باشا يعني بابلين because the circuit is closed, we have a closed loop. كاتا كرنتك بناو أو سيركتي داغرواتن باشا أو كرنت بابا it will produce يعني induce its own magnetic field باشا كاتا قلت مالي reflex كده غوري EMF درس دبي أو EMF pushes the charges through the circuit كاتا current is induced باشا IN يعني induced which is generated أو كرنتي كابنا كل كده ترى بابا it will induce يعني produce its own magnetic field اللي رد هون بلم it becomes chapter 5 قلت ما نقول كرنتك بنا كل كده برا or solenoid here there will be a magnetic field around it باشا كاكا أو magnetic field ده what is the nature of this magnetic field كاكا ما اللي رستا ككرنتك بناو كل كده ترى there will be a magnetic field around this coil here باشا بس قال لي ببابا أو magnetic field they إيه الدروس بوا باشا the magnetic field that is induced will always oppose the magnetic field that created this باشا كاتا أو magnetic field they induce ببابا which is chapter 5 we can say that it opposes the magnetic field of the one that created this which is of a bar magnet باشا كاتا bar magnet طاني بلين أو magnetic field كا induce بو تازه درس بو opposing magnetic field بار magnetic كي دكا لبرت سبابت كا magnetic field بار magnetic كي أو magnetic field درس كي بس باشا if they oppose one another like how do you think they'll oppose one another باشا again if they oppose one another يعني سبابة and these two magnetic fields will be in a way such that they oppose or will be opposite at this point here or how do they oppose one another كاكا oppose ما بس مانت يعني ريجريلي دكا بابا باشا so again magnetic field دكا you can see that direction of magnetic field here in this direction and bubble is in this direction here كاتا this magnetic field must also be in this direction so that it can oppose one another باشا because that is how it is بس باشا استاكا if we move this one a little bit away so that we could do these numbers a little bit fine here that's too much I guess but let's just move this one away even though but we're trying to see if we could do this one properly here or see how they oppose one another لأن كان لي عندك تكلبوا قلت معن أو direction magnetic field كان بابا how does it exactly oppose one another اللي رشكتك so that you know how it is how do you think these two are opposing one another again magnetic field يويلو يربي بابا got that magnetic field يوان will also be you can see in opposite direction here so that these two will oppose one another. In other words, كاكا بكردي كيان بابلون بمختصري بابا أجر إيرا north بيتن ليرش دبيت north باشا أجر إيرا north بيتن لكن دي كده بيت تصير دبيت south and that is chapter 5. As that based on this north and south that is induced كاكا we can tell which way the current is flowing through the circuit. باشا ما chapter 5 دمانجو بابا align your forefinger in the direction of a magnetic in the direction of current. Your thumb will always be north. أو زارشتك عكسه. Because we already have north, كاتا بافنزي قولة رويل north بي, then your four fingers would be in the direction of electrical field. This أقرأ هذا غلطة because north is at the other side, and we said that always use the front of a coil. If I do this one now here, you can see that hopefully. My thumb is pointing north كاتا direction كرنتكي at the front view of a coil direction كله شندرة. It is moving downward. Kata, according to this baba, direction it is pointing downward. Again, point downward be this is how it goes. Kata galvanometer it will shift to the right side. باش كاكا است diagram كله دوباره دكموه حتى واضح تريان رون تربيتن بس كوب زانم direction galvanometer it will shift and move to the right كاكا. هم زاري بابا we can say the needle will always باشا the needle of the galvanometer will always shift basha let's say in the direction of a current in the direction to the direction of the current in the direction of current in the direction of current يعني تسبابه but picture اللي بير كيبا وشلو هندق explain كم أو direction galvanometer بابلن need look here if the current is flowing this way كاكا وكو بابلن تزانم درجة حسابك if the current is pushing this way, if it is pushing this way, this is how it goes. Just like, for example, this is what it is. The current is flowing this way, so this is how it is shifting. If the current is flowing in this direction, this is how it pushes, kind of like, right? And then what if the current is in the opposite direction? What do you think the galvanometer, or how the galvanometer needle will shift? Push it, so it's like a door now. Once you push, this is how it is going to shift. Now, knowing which direction the galvanometer is shifting, it is very important. Direction current كي بابا قال لي بي بقعد لو دوباره كموليرا باشا قلت معنا كويلك مانيا أو direction بابلن. This is how the wires are wound, let's say, around the coil. Malira a magnet did pressure north and south. Man, this is the direction of the magnetic field of this. I got a bono I bit baba. But man, that induces a current here. Good man. Oh, there would be. So let's draw here. Now there will be a magnetic field. As this magnet is getting closer, there will be a magnetic field around this coil. And directionally, a magnetic field that is induced will be in a way such that it always opposes the magnetic field that created this one. Basha. North north, because north and north oppose one another. This is how they oppose, repel. Agar south agar south buba, it would have attracted. There's no opposition agar north beaten south. Adi direction could be more north beaten baba. Whatever the direction, whatever your forefinger is pointing, that would be the direction of the current. Because this side is north, the direction of the current is downward. Keep following the line here. This is how it goes. Pushes the galvanometer, shifts the galvanometer this way. This galvanometer needle is now shifting to the right, and then the current keeps flowing there. Because these two magnetic fields are opposite here, as it is getting closer, magnetic field that are crossing the coil increases. Direction magnetic field, the outside, the two, these are what? These are the same direction or opposite direction? Opposite. Net magnetic field, the net external magnetic field. The net external magnetic field, because these two in the opposite direction, they cancel each other. Magnetic field line outside the two will decrease because they are in opposite direction. But the magnetic field that are crossing through the coil increases to magnetica which you saw, which I believe you saw it here. Basha, this is exactly what happens here. Bashkaka. What twani zor kurtishikir baba asanibka. Harkata gutman. Yagar magnetaka hata pesha. Like if it is moving towards the coil, lokati. Same poles will always face one another. Basha. أول خد لك ناخد بنو سبابة قلنا ملزمة كدانية. باشا. هاد ملزمة شي بكار ديني. ما ليرة. If doesn't matter which the pole is getting closer. If the magnet is getting closer to the coil, and if they're getting closer to one another, Baba, we'll have the same poles facing each other. Basha. If it is getting closer, Basha, both magnet and the coil will have the same pole. Basha. If getting closer, closer, we'll say same poles face each other. Same poles face each other. هو يعني تسكاكا بتماني يعني أجر north بيتا بيشة إرش دبيتا north بابا باشا أجر south بيتا بيشة إرش دبيتا south. But once they're getting closer to one another. أجر لو خالبي. Now let's try this, but we'll do the reverse outside. Reverse كما بس مانتيا. If this time, if the magnet is moving away from the coil here, this is the coil here. A galvanometer again, there's a closed circuit here. On outside of the magnet is moving away from the coil. It is this time moving away. Moving away and it is so these are the magnetic field lines here. From north to south. Stajmari magnetic field line for example, that we're entering the coil لستا because it is moving away. لستا أو جماري أو magnetic field داني that we're inside the coil now because this is moving away. كاتا جماري magnetic field line كان أواني كوا بناو كويلة كده دورن بابا زيادة كيان كم دكاتنا لستا أو magnetic field line أنا ناو كويلة كرا دردين بابا كده ناو كويلة كده درات كاتا دلين the magnetic field line and the intensity of magnetic field line through the coil and within the coil decrease. جماري أو magnetic field line كوا بناو كويلة كده تبرد من كم دكا. Why? Because the magnet is moving away. أو خالي كم باشا. As the number of magnetic field line are moving away كاكا because magnetic move away ده بيدور دكيتو كواتا. Will there be a change in a magnetic flux or not? Of course. Magnetic flux سبو جماري أو line أنا كوا بناو كويلة كده دوران which is our right angle you can say. ستا جماري كم بو. That means the flux or magnetic flux is change. أجر magnetic flux change بيقول من يما فقدرز دبي أو يما فد وذكا كرنتك induce بي باش بابا أو كرنتك induce بو it will have its own magnetic field أقال لي بي بابا ما نستعكنا أو كرنتي بناو كل كده درا it will have a magnetic field around this coil باشا it will have a magnetic field around the coil باش لابين ستا magnetic field that you hear it will be induced around the coil. Dubara, a magnetic field there will oppose Basha will oppose to the change bubbling in the magnetic field of the bar magnet. Will oppose the change in the magnetic field of a bar magnet. دبا لو يديك شنو سيبام change of magnetic field of a bar magnet. Basha. Oh, it is more scientific. Yeah, Basha. This time, Baba. How do you oppose or how do you think this two oppose one another? Sta magnet بخوي لي يدور دكريتو بابا. أجد استاك ليرة كاتا أو magnetic field there. When esta, of course, one side will be north and the other side will be south. But how do you think they're going to oppose one another? This time, because this one is moving away, so this magnet, and magnetic field, is trying to pull it back. And how do you? Because it doesn't want it to go away. So how do you think this can oppose that? How do you think this coil can stop the magnet by being the same pole and opposite pole, Baba? It's same pole between north and north repel the it even push it further away. There's no opposition. But this time here, Baba, outside the bit to south, the bit to north, the bit to south, because now south and north it tries to attract one another. This is how this induced magnetic field tries to oppose the field of the bar magnet here by becoming opposite poles. Opposite nabi Baba. It cannot pull it back. أقال لي بباشا يباشا قرير south بيت نير north direction magnetic field because of course is always going from north to south. قلت ما ليرة اللي ناو اللي جوري اللي ناو كويلة كي جمارين magnetic field line كان كم دبيتو because it is moving away. بس قلت ما شاد دريب كي بابا the external magnetic field or called external magnetic field دي دري كويلة كي باشا. تيلي دي بابا you can see that these are both in the same direction when you we know that if two fields are in the same direction, كواتا نتكي an external magnetic field line كبا وتيلي دي زيادة كواتا we can say that the external magnetic field outside the two coil increases بابا أقال ليبي باشا استاكا دوبارة لاك north لاك south كواتا كو بزانم direction كرنتكي كو أوزاري أما نمانغو بابا always point your thumb to the north the direction current. If that is the case, the direction of a current, the front view here is going to be upward. Right? This is going to be the direction of a current here. This time here, the current is pushing the magnetic, the needle of a galvanometer this way. This time, the galvanometer needle it is going to shift to the left side here. And then this is how it will continue. Basha. Galabid bubi got mani kamzarake. Direction galvanometer needle it will shift to the right because the magnet is moving away. It is going to shift to the left. Bash baba agalibi. Woku samari the twanin blend. If the magnet is receding, which means moving away from a coil kaka. Woku samari chibaba odushte bzana. Ba widikash lo dubara da kamo. If a magnet is getting closer from a coil kaka, if it is getting closer, they will have the same pole. North, north. If it is getting closer, because these two will oppose one another. But if it is moving away, Okati, they will have opposite poles, Basha. If moving away, what's a magnetic? If it is moving away, Okati, they will have opposite poles. Yani can the magnet, Basha, magnet and the coil will have opposite poles. Especially the mango agarbeta pesha, they will have the same poles, bashkaka. But now if it is moving away, they will have opposite pole. Agalera north bilera the beta south. Agalera south beokati the beta north beat. And this is so once it is moving away, they will have opposite poles. Agad lo khala nabi baba zoso gringa kata. What we have done is basically but manager magnetic beta pesha, and if it is moving away, okati EMF current the two magnetic fields will oppose one another. Basha, at every case here, Gutman, of course, we can use that to find the direction of the current. أو جدتواني blend lenses law باش بابا بس تاستا أقال لي بتنها باسي direction current إذا كان هيتس باسي أو EMF ما نكرديك that will be induced in this coil here. Basha Wrya, the lenses law, it is used to find the direction of the current, which is going to be next in more details, inshallah. When a bar magnet is pushed into a coil of wire, the strength of a magnetic field within the coil increases. A magnetic field a current is induced in a coil due to the change in a magnetic field strength. It will be induced inside this coil right here. This induced current in turn produces its own magnetic field. It will induce its own magnetic field. And the induced magnetic field opposes the increasing strength of the applied field. Field there keeps getting closer and increases. These two will oppose one another. A magnetic field it will not oppose this magnetic field. It will oppose the change in this field. It doesn't attract or repel. If there's no motion, there is no attraction or repulsion, because there will be no EMF. There's nothing here to be induced. There's no magnet to repel the other magnet or to attract it. This EMF, magnetic field, it will oppose the change of this magnetic field. Magnetic field, then they will oppose one another. If it doesn't move, there is nothing to oppose. The direction. The induced magnetic field opposes the increasing field of the approaching field, of the bar magnets, approaching field. The direction of the two field is opposite. But outside. And the outside direction to field is, you can see that outside because these are opposite, they will cancel each other out, sort of, we can say. The external magnetic field decreases. Magnetic field because they're opposite. The coil and the approaching magnetic field create a pair of forces. They repel one another. They will have the same pole. If this is north, this is north. If this is south, this will be south. And these two obviously will repel. Oppose one another, repel one another. So when approaching, the two magnets have the same pole. When a bar magnet moves toward a coil, the induced EMF is similar to that of a bar magnet with the orientation shown here. And the field directions are opposite here. There is that one direction. Now the next thing here, what happened when a bar magnet is moved away from a coil? That'll be next. Alright, when a bar magnet is moved away from a coil, the magnetic field within the coil, inside the coil decreases. As this magnet moves away, as this magnet is moving away, magnetic field they're pulled out. Magnetic field decreases. يعني دتوانين بلين زور باش كاتا current is induced because that changes the flux or magnetic flux. Current induced the induced current will produce its own magnetic field around the magnet, obviously. Now it's that the induced magnetic field opposes the decrease in the strength of the receding magnet. But a receding magnet يعني أو magnetic field there that is moving away باشا moving away باشا decreases the strength of the moving away field باشا and the field of the moving magnet moving away magnet receding يعني أو field إيكوا كم دكات باشا يعني كم دكا what's the field دكا خالي depends on the direction of the two field that can be increased. Why is that, Baba? Because now, how do you think these two can oppose one another? Good man, a north beaten, the be a south beat so that it attracts it so that it doesn't let it go. And Basha Okati, it is south beaten. This is how the direction of a magnetic field would be. And these two, obviously now it is going to be the same direction. When you got that same direction, Baba, the external magnetic field will increase because these are both in the same direction. We add them up. Basha. The coil on the receding magnet, or magnete that is moving away, create a pair of forces, but this time they must attract one another in order not to let it go, in order to oppose that. Basha. When moving away the two magnets have an opposite pole facing each other. Basha. And create a pair of forces that attract one another. Basha. Again, maybe. Oh, the Tony Blaine Zozo getting the Baba. This is basically all about, you can say, Lenz's law, which is used to determine the direction of a current. Let's say Lenz's law came about. Lenz's law, Lenz was a scientist also, you can say that. He said that, and states that the magnetic field of the induced current will always be, Basha, in a direction opposite to the change that created that current, Basha, and that magnetic field here. Divided the kind of Lenz, Tsigo, the magnetic field of the induced current أو magnetic field the magnetic field أو current induced بوا يعني درست بوا generate بوا will always be in a direction but direction activated such that it is opposite to the change that created this one here. ما بس مانتي opposite رنگ قبل ما وصل لو دلنا opposite خو لدوام حالة ليرة direction كان opposite نبو same direction بابا كدلنا opposite ما بس مان it is in a direction such that it is like it is in a direction in a way such that it is always opposite to how the magnet is moving away. If it is moving closer, it will be in a way such that it repel that. Isn't that opposite? Yes. If it is moving away, it will be in a direction to pull it, like to pull the magnet closer and fill the closer, so that'll be opposite. Or this is what it means here to be opposite to the change that created that magnetic field. That is what exactly we mean. If it is getting closer, they will have the same poles, Basha. But if it is moving away, they will have opposite poles. It doesn't matter what poles it is. These are very important. The first thing that we have says Lenz's law that is used to find the direction of a current only. Direction that is induced, that is generated here, that is produced here. But we've never talked about the magnitude, how much current is induced. That Lenz's law that is used only to find the direction of the current here. The field of the induced current does not oppose the applied field, but rather the change of the applied field here. طلبة بابا ليرة عندك إشكال اللي يدرس دبيت الله أو خالة ما بستيتشا. قلت man بابا ليرة أو magnetic field إيكوا درس دبيت in here. For example, once we have a coil, باشا. أو coil لك قلت man this magnetic field that is induced here does not oppose the magnetic field of this magnet, باشا. It only opposes the change in this field. That is should be opposite. Man. When does this two oppose one another? When there is a relative motion. Only if this magnet is getting closer or moving away, then this two, let's say magnetic field, will oppose one another. This magnetic field here, it does not oppose this field. It only opposes when this field is changing. أجر ناخذ بتمان دكرية magnetic يعني أو بار magnetic لنا كويلة كي دابني there would be no EMF اگر هیچ EMF نبود there would be no field to oppose or to push it or pull it here باشا اگر لو خالی بی کاتا أو كاتا oppose جديدة كان when this field is changing أو تذكري change by getting closer and moving away تذكري rotate بهرشتك بمهم only when this field is changing then they will oppose one another. That is what we mean by this. خالص دي كش كازو جرينجا if the applied field change باشا أو applied field دي بابا جرو change بيتن. Alright, the induced EMF here, يعني بابلين the induced field always try to keep the total the same. Oh yeah, and this is something very important and also been in Nuzari as well. And that is, you could say, that is based on, we can say, the law of conservation of energy. Here, for example, no magnetic here, north and south, and this is the coil. That's the galvanometer. And if this magnet is getting closer, okay, جماري field كان زيادة كونيا باشا جماري field كان زيادة in this coil here, man, like isn't that violating the law of conservation of energy? Yes, كاتا لو حالتي بابا أو magnetic field equal induced be will always be in a direction such that it keeps the total the same. ليرة كمان جماري أو magnetic field داني كوادين بناكو لكذا تبرد بن بابا زيادة كات من كاتا. This one has to be in opposite direction here. عفوا. Has to be the other way around. Has to be in opposite direction to keep the total the same. Magnetic field كان زيادة. This two must be in opposite direction here, the one that is induced, so that or tries to keep the total the same as much as possible. What about when it's moving away? كاتك move away دبي بابا. Magnetic field it is decreasing here, so this one here is going to be in the same direction. This one is going to be in the same direction to keep the total the same, so that not to let it decrease. So ما بس معناه ليرة field زيادة دبي أو دبي opposite هتا to keep the total the same. ليرة field كم دبي. This one is going to be, or it will be in the same direction to keep the total the same from decreasing furthermore. So this is what happens. The induced field always tend to keep the total field strength constant on the لخد underline because this is something very, very important. Khali Sam says Lenz's law, which we said it, does not provide any information about the magnitude of the induced current. It only talks about the direction we said. Khali Taram also, it is important, Lenz's law illustrates the principle of energy conservation. Illustrate answer to it applies or shows shows the principle of energy conservation. How does it do that? The induced EMF will be, the induced magnetic field will be opposite to keep the total the same. That will be the same direction to keep it the same as much as possible. This is how it illustrates the law of conservation of energy of the magnetic field. The magnetic field induced of the induced current in a direction is in a direction opposite to the change that created this one. Who said this, Kaka? Right? We said that. Was it Faraday? No. Lenz's law? Yes. Ohm's law? No. Ampere's law? It is not. According to Lenz's law, if the magnetic applied field or field applied to a circuit changes, the induced field will always tries to keep the total field constant, increase, decrease, or none of them. We said it always tried to keep the total constant. According to Lenz's law, if the applied electric field change, the induced field attempt to keep the total field strength and strength constant. The induced field attempts to increase the total field, attempts to decrease the total, or the induced field attempts to oscillate about an equilibrium value. It always tries to, or attempts to, keep the total field strength constant on Hami. That is related to the question that to the concept that you just saw. According to Lenz's law, if the applied magnetic field on a circuit is changed, the applied field tends to make, or the induced field tends to keep the total constant the same on Hami yakshta. بسارة دي كمان هذا explain the lens and how Lenz's law allows you to determine the direction of the induced current here. Man, how does Lenz's law allows you to find the direction of a current? Lenz's law states that the induced current in a circuit will always be in a direction and flow in a direction such that it opposes the magnetic field such that it opposes and the magnetic bubbling such that it is magnetic field will always oppose the change in the magnetic flux that caused this magnetic field induced. This is how. If it is getting closer, they will have same pole. Agar bżani pole kan chan side north, chan side south, then you can easily tell how or which way the current is flowing. This is how you could do that. بس يوشمان كردبو needle bubbling needle galvanometry it will always in a direction of the current flow. Shifts in the direction of the current flow. Man كرنتك بچان لا يدابروا needlك لأولايا shift دبيتن. بساري بين زمانية ضل rapidly أقال ليبي rapidly inserting the north pole of a bar magnet into a coil of wire connected to a galvanometer caused the needle of the galvanometer to deflect to the right. Kawata agar north pole magnet inserted into a coil of wire that man galvanometer it will deflect to the right. Agar low khalib yani northaka wadaka needlaka shift to the right. Basha, what will happen to the needle if you do the following? Basha? Need like a if we do the following. The first one, if we pull the magnet out of a coil, basha. North now coil it will shift to the right one. What happens if you pull the magnet out? Need like a shifty shift to the left, obviously. So what is this is what the question is saying. If the north is shifting or let's say inserted into the coil, the galvanometer will shift to the right. That's what the question is saying. What happens if the magnet is pulled out? Got that? This would be what we have. There's a bunch of them, by the way. So this is the thing that you need to know here. If the magnet is pulled out, if it is to the right, the be to left. Because direction motion is reversible. If the magnet is, or let the magnet sit at rest. Sit at rest, if the magnet is not moving. If the magnet, this is A. If the magnet is not moving, the galvanometer needle will point to 0. That means there's no EMF induced one, That would be the second one, or this diagram right here. C says, if you thrust the south end of the magnet into the coil, it will shift to the right. What happens if the south moves into the coil? Obviously, because you've switched the poles now. If south goes into the coil, the galvanometer needle will shift to the left, which is opposite to what is given here. These are easy enough, right? Khali Shashamdala explained how Lenz's law illustrates the principle of energy conservation by opposing the change in the external magnetic field. When the induced magnetic field prevents the energy of the system from increasing or decreasing. How does it prevent the energy of a system to increase or decrease? If it is getting closer, the two fields, the one that is on the coil. So how do you keep it the same? By making the induced EMF, by making the induced field to be opposite, so that they cancel each other out, so that it stops the field, the total field, from increasing. What about when it is moving away? External so how do you keep that from changing? The induced has to be in the same direction as the field of the magnet that is moving away to keep the total the same. By opposing the change in the external field around the bus. Does dropping a strong magnet down a long copper tube induces a current in the tube? If so, what effect will the induced current have on the motion of the magnet here? Later, I think it would be best if we see this one first and then get back to this question right here. All right, and then we'll leave this one for later. إذا ماشي فيديو كامل perhaps maybe we'll have to, or we'll see a little bit more than that, just to see, for example, like how are these things working here. The first thing that we have later, we can have this one بابا قليلة تماشاتشكي. This is what we've mentioned earlier. If this magnet is getting closer or away from the coil, then there would be a current will be induced inside the coil here, and this is how you can see that, Basha. This is like a short video. In either cases, this lamp you can see here, or this light bulb, will glow, and you can see the galvanometer shifts right and left depending on how you're going to move the magnet, whether closer or away from that. There's also more, actually, if we want to, like this one here. This is will take us a little bit back to chapter 5 too, but I think it's worth watching too. Chapter 5, if we have a battery that provides current through a circuit, baba, there will be a magnetic field around the coil. When you're starting from a wire, conductor current there will be a magnetic field around this one, but if we turn that into a loop of wire, the magnetic field would become stronger. Now it is a coil. Of course, the magnetic field of a coil is stronger than just a wire, because now it's a magnetic field. We concentrate inside the coil. Of course, you can see that there is more. If we just do that, for example, if you have more loops, there will be a magnetic field from each one of these magnetic field and combined them, and so the magnetic field from a solenoid would look like, or the same as a magnetic field line of the bar magnet. North, south. This is what happens when a current flows through a coil of wire, a solenoid. Well, we also talked about, for example, electromagnetic induction. So obviously Faraday, like he said, that the EMF induced in a circuit, which is going to be later, it is directly proportional to the rate of change of magnetic flux. Magnetic flux which is next, by the way, but you can see here, when this magnet is getting closer to the coil or away, you can see the galvanometer needle is shifting. There is this light bulb, which it tells you that EMF is induced. You can see that. This is how it works, as you can see. These are what we have so far, you can say. Now let's go back and watch the other one. What happens once we all right, I think it is ready to be watched. So I want to take a look at this. First of all, we're going to drop an iron ball into this copper tube, you can see. The iron, obviously, the iron ball is going to fall just normally, and then we'll try this with the magnet, and you try to see what are the differences, So here you can see that this is going to drop real quick into this, and then we're going to look at it from the top view as well to see how it happens if we use a magnet. So this is a spherical magnet, same size, by the way. If you drop this one, it's going to take a long time, and you can, by the way, there's no slow motion here. This is just normally, it takes about 4 seconds to get to the bottom here. So what exactly happens here? I want you to focus on this, This is the top view here. You can see that how slow it is going to fall. But what exactly happens, or why does this happen here? That is because as this magnet is falling here, because now the magnetic flux is changing, and you can see that this is a closed copper pipe here, according to, of course, the surrounding here. This change in a magnetic flux produces a pair of forces here. If a magnet is getting closer, from the top and bottom here, right? Let me pause this perhaps, So this point here, as this magnet is moving closer, at this side here, of course, there will be a current here. This current, these are circular current here. Would produce its own magnetic field, but because this is getting closer, these two magnetic fields will be in a way such that they oppose one another. These are both north because they try to repel one another. Because this part of a magnet is moving away here, at this point here, there will also be a current here. Because this is south, magnetic field would be in a direction such that this is north here, because this magnet is moving away, so this one does not let it move away or oppose that. So there is an attraction force here. It tries to attract it, not let it go. And there's a repulsion force here. It does not let it get closer here. So these two forces, of course, will slow the motion of the magnet down. So at this point here, we can see that this magnetic force will be equal to the gravitational force in here. So this is why this magnet is now falling at a constant speed inside the copper pipe. Why? Moshni او magnetai لناو copper pipe ودك كرنتك لناو دروس ببابا او كرنتها will make the magnet bubble, and it will have its own magnetic field. A magnetic field there will always oppose the two ends of bubbling of a magnet, which makes it slow down inside the copper pipe. بس اگر لیبی بابا گفتمان اگر یک خالدی کشه, if this copper pipe is it is broken, and if there is a crack in it from the top to the bottom, from the top to the bottom, then this phenomenon does not happen. If this copper pipe has a crack in it from top bottom, if it is not a closed loop, this cannot happen. The magnet would fall just fine. Let's go back to the question. It says, does dropping a strong magnet down a long copper pipe induce a current? As you saw, of course, yes, Basha. If so, what effect will the induced current have on the motion of the magnet? It makes it slow down, because this magnetic field that is induced here will be in a direction such that it opposes this change, Basha. It will oppose the magnetic field of the normal magnet, this bar magnet. As a result, it will slow down. So yes, the field of the induced current will oppose the magnetic field of the magnet, bar magnet, whatever the magnet is, the type of the magnet. The opposing magnetic field slows the motion of the magnet inside the copper tube. But Gutman agar pipe was not closed, then the current will not be induced, then the magnet will never slow down. But let's say two bar magnets are placed side by side so that the north pole of one magnet, it is next to the south pole of the other magnet. If these magnets are then pushed or inserted towards the coil of wire, would you expect an EMF to be induced? Explain your answer. As you can see here, it's got magnetic field. Yak magnet will be cancelled by the magnetic field of the other one. Because these two poles are opposite, the magnetic field of one magnet will be cancelled by the magnetic field of the other magnet. As a result, it is the same as if there is no magnet inserted. If there is no magnet inserted, nothing inserted, no EMF will be induced. Right hand rule, how do you tell which way is the current flowing and which way the needle is shifting? They will always have the same pole. If the magnet is getting closer, it's the north this side would be north. North be now direction magnetic field, it is upward in here. So if you follow the path, you'll see that this is how the coil is shifting, or the galvanometer needle is shifting. What about this one here? It's moving away, as you can see. If it is moving away, that will have opposite pole. North be south, south north, and by using this, make sure that your thumb is pointing north. It's downward front view of a coil. Follow the path, you can see which way the galvanometer needle is shifting. Because that affects how the current is flowing through the current here. So north that has to be upward. When upward direction Madam Bono we'll just like Madam Lera upward the kata the Bono this is how it is going. When kata obviously it is going from this side to this side, which is shifting to this. We're gonna have the 20 lira ويكي كاتا لخواري هر بس واسان طريقة تماشا چيرك there if it is this side is north kata direction كاوت زارة بابا it is downward madam downward you can see that here is downward kata this is how it is going get تماشا چكي so it pushes the galvanometer needle this way this is how it is going باشا هذا وين ده هي سيدي كي تداري how we use the right hand rule وديكا أسانا وبزمو برسارة ليب قرن لو زاري دابي تسكا برسارة تشيزوزو قرنجة تسندين زاريش لو زاري هاتي توبا no video تانزو اللي دريش نميتو I believe that'll be the end for this session. Stay tuned for more videos inshallah. Assalamu alaikum wa rahmatullah.